Here we have a general circle with center HK and radius R. I've shown the circle in this quadrant, but I could have shown it anywhere. We're going to be interested in the relationship between the coordinates of any point on the circle, that's x and y, and R, the radius, and theta, where theta is measured anti-clockwise from the positive x-axis to the radius line. Now, I've positioned xy on the circle in such a way that theta is an acute angle. That is an angle between 0 and 90 degrees. So I'm going to look at the situation for this particular case, but it will also hold for situations where xy, say, is over here. If xy is here, then theta is going to be an obtuse angle. That is an angle between 90 and 180 degrees. Or if, say, xy is here, then theta is a reflex angle, an angle between 180 and 270 degrees. So everything I will say will hold for those situations. It's just convenient to work with this right angle triangle. So to find the connection between x, y, r and theta, we're going to get the two short sides of this right angle triangle. So theta is an acute angle in this right angle triangle. We know that the cos of theta is the side adjacent to theta, which I'll just write ADJ for short, divided by the hypotenuse, which has length equal to the radius. So we can see then that the length of the adjacent is r times cos theta. Similarly, for a right angle triangle, the sine of theta is the side opposite theta, we just call it OPP for now, divided by the hypotenuse, which is r. So the side opposite theta, this side here, is r times sine theta. Now let's look at x. Well, we see that the distance from the origin to this value here is h, and the distance between here and here is r cos theta. So it's easy to see that when theta is an acute angle, that x is equal to h plus r cos theta. Similarly, we can find y in terms of r and theta. The distance from here to here is k, that's the y value of the center. And if we add on r sine theta, we will have the y value of this point. So y is equal to the y value of the center plus this side of the right angle triangle. So this is very clear when theta is an acute angle. But these relations also hold when theta is any angle between 0 and 360 degrees. So for example, if the point xy happens to be here, we can see that theta is an obtuse angle, an angle between 90 and 180 degrees. So what happens to these relations? Well, the cos of an obtuse angle is negative. So the x value of this point will be h, which is the distance to the center of the circle, the horizontal distance to the center of the circle from the origin. But we will have to subtract off this distance. The fact that cos theta is negative will take care of that. So you can take my word for it that these relations hold for any value of theta. It's just an application of trigonometry for angles theta that are greater than 90 degrees. You can think of the unit circle. Well, this isn't a unit circle actually, it's a circle radius r, whereas a unit circle has a radius of 1. It's just a scale version of a unit circle. And anyway, these results will hold. And we'll see more about that now soon when we try to get back the original version for the equation of a circle from these equations. So these two equations are often called the parametric form of the equation of a circle, because x and y depend on a single variable or parameter theta, where theta is an angle between 0 and 360 degrees. So the independent variable in each of these equations can be thought of as theta. H, K and R are fixed values, they're constants. So to generate points on our circle, we just need to plug in different values of theta. Of course, we're not constricted to this range shown here. I could pick a value greater than 360 degrees, it doesn't matter. But if we take all values of theta from 0 to 360 degrees, we will generate all the points on the circle. Of course, as I said earlier, if the parametric form does indeed give the equation of this circle, then we should be able to derive the original form of the equation of a circle from this. To do that, we isolate cos theta and sin theta in both equations. If we isolate cos theta in the top equation, we get x minus h over r equals cos theta. And if we isolate sin theta in the second equation, we get y minus k divided by r equals sin theta. Why do we do that? Well, we are going to square both sides of these two equations. And we're going to sum both sides as well. So if we take the top equation and square it, we get x minus h squared over r squared equals cos squared theta. We do the same with the second equation. Now let's add both of these equations to each other. Let's add the left hand sides and then add the right hand sides. So if we add these two together, we get x minus h squared over r. I'll write it like this. This one here is y minus k over r all squared equals cos squared theta plus sin squared theta. But cos squared theta plus sin squared theta equals 1 for any value of theta. So this is an identity. Now, we can multiply this equation by r squared. R squared times 1 is r squared. And here we have the familiar formula for the equation of a circle. So we had to use this well-known trigonometric identity to show that the parametric form of the equation of a circle does indeed give us the familiar or Cartesian form for the equation of a circle. So the Cartesian form gives us the connection between x and y, whereas the parametric form gives us x and y in terms of a single parameter theta. Let's take an example. We want the parametric form of the equation of a circle with radius 3 and center 7, 5. Well, that's the circle in the diagram actually. So the radius of this circle is 3. The center HK is 7, 5. So this is straightforward. X equals H, which is 7, plus R, which is 3, times cos theta. To get Y, we have K, which is 5, plus R, which is 3, times sin theta. So this is it. These two equations constitute the parametric form of the equation of a circle. Let's just generate some points on this circle by taking values of theta. Let's say theta is 0 degrees. Well, what do we get for x? Well, if we plug 0 in for theta, we have the cos of 0, which is 1. So we get 7 plus 3 times 1, which is 10. What about y? Well, y is 5 plus 3 times the sine of 0. The sine of 0 is 0, so we get y equals 5 plus 3 times 0, which is 5. So we have the point with coordinates 10, 5. Let's look at that point on our diagram. Well, It's this point here actually. We go out 10 units and we go up 5 units. So this point here corresponds to a value of theta equal to 0. So if we draw in the radius line to this point, the angle between the radius line and the positive x-axis is 0. It's not surprising. Let's take theta equal to 90 degrees. That should give us the coordinates of the top or highest point of the circle. The cos of 90 is 0, so we have 7 plus 3 times 0, which is 7. The sine of 90 is 1, so we get y equals 5 plus 3 times 1, which is 8. So this point has coordinates 7, 8. Let's look at the coordinates of this point here. Well, this point corresponds to theta equals 180 degrees. If we draw in the radius line and get theta, which is measured anti-clockwise from the positive x-axis, we see that theta is 180 degrees. We can actually read off the coordinates of this point. We can see that they are 4, 5. So I'll just write that in. Let's just work it out from the equations. When theta is 90 degrees, or sorry, 180 degrees, the cos of 180 degrees is actually minus 1. So we get 7 plus 3 times minus 1. 7 minus 3 is 4. Just as we have here. As for y, we have the sine of 180 degrees is 0. So we have 5 plus 3 times 0, which is 5. So we get the 0.45, as you can see. Let's just do one more. I'm just taking basically all the angles that define the 4 quadrants. So let's take theta equals 270 degrees. Well, we can actually read this off. We can see that the y value, or sorry, the x value is 7. The y value is 2. We plug 270 in here. The cos of 270 degrees is actually 0. So we get x equals 7 plus 3 times 0, which is 7. As for y, the sine of 270 degrees is actually minus 1. So we have 5 plus 3 times minus 1. 5 minus 3 is 2. Of course, we can pick any value we like between theta and 360 degrees. It's just that these 4 values are the easiest to show on a diagram. Well, at least for this particular circle.